All right, let me scroll up here a little bit, and let me take some time and walk back through our derivation. I know it's been a long time since we looked at this, but I wanted to take our time and digest what we did. The main reason being is that we are going to, you all, are going to be doing this for homework here in the not too distant future. So real quick, let me walk you through a couple things. So we started off with an element and we said, okay, let's take a look at what its displaced shape should look like. And it should look something about like this. We call that v of x. And v of x is going to be dependent upon the translations at each joint, v1 and v2, and the rotations at each joint, v1, v2. Now, I can't stress this enough. One of the things that is true only for beams, since we're concerned with displacement compatibility from a rotation standpoint as well, when we look at beams, not only do we consider the function, but we consider the derivative of the function. We don't do that for bars. And that's important to note because you all are going to do this on your homework for a bar. Okay? So we said, okay, we've got these four unknown constants. We defined a cubic function because we figured we've got four constants that define the displacement of this function. A cubic function seems to make the most sense. We say, all right, we got four boundary conditions. And we take those boundary conditions and we evaluate them one at a time. Now, the first two are easy. The second two, not so much, because the second two give us a true set of two equations and two unknowns. I mean, theoretically, you are dealing with four equations and four unknowns, but the first two are pretty much directly solved for. It's the last two you actually have to do a little bit of matrix math to figure out what C2 and C3 are. And I know it turns into a little bit of alphabet soup, but you kind of have to just go through and do it. I promise you that your homework isn't as bad. Okay? So two equations and two unknowns in matrix form, that's what we've got. And if you've got a matrix inverse and it's 2 by 2, you say 1 over the determinant, and then you swap those terms, change the sign of the other two. So we went through, we did all the algebra. I know it was a lot of grunting, plugging and chugging. But in the end, we get our two constants, plug and chug. Our displacement function gets to be a bit messy, but if we start factoring it in terms of our nodal displacements and translations, we get a pile of junk times v1, a pile of junk times theta 1, a pile of junk times v2, etc. Those pile of junks, if you will, are our shape functions. And those are our shape functions, the n1, n2, n3, and n4. Okay? So everybody was all right with that. Okay? So that's a lot of work going into that, but it is an important step. Now, one of the interesting things to point out is that this difference, and this is going to be important on your homework, the difference between bar mechanics and beam mechanics is when we were transitioning from an N matrix to a B matrix, two things were true. Number one, this little y term stuck out because what we were dealing with was sigma equals my over I. The stress varies over the depth of the beam, so the strain varies as well. So we have this y term left out. And then because of the mechanics associated with beams, for bars, we were taking the first derivative of our shape functions. For beams, we're taking the second derivative. Okay? So we had each of those functions. We said, all right, we can take the second derivative. Here's n1, so there's n1 prime and n2 double prime. And if you grunt it out, b1, b2, b3, b4, your B matrix is y times those functions. Okay? Pretty straightforward. Not too bad, right? So now, based on our formulation, the stiffness matrix is the volume integral of B transpose CB. C is simply just, for this element, just the modulus of elasticity, or just E, Young's modulus. So that C can come out. So we have the volume integral of B transpose times B. And then if you look at B transpose times B, because of that y term, you're going to get a y squared. Okay? So if you look at this and splitting it up in not just volume integrals, but an area integral and then integrate that over the length, the area integral of y squared has a very special name. We call that a moment of inertia. So that, lo and behold, dun dun dun, is our stiffness matrix for a beam. I know it seems pretty But if you actually start going through one by one and do each one of these terms, you will get the same stiffness matrix as you did before. Okay? And we tried that out on the first term, and we got 12 EI over L cubed, which is the first term in a beam stiffness matrix. Now, what I want to do is I want to continue this a little bit, and I just want to show you one thing, that these shape functions and beam functions and what have you, particularly the shape functions, the N matrix, has a little bit more applicability than you might think. And I'm going to show you something. Okay. So is everybody okay with what we've done so far? Does anybody have any questions? Okay. Now, all this stuff that we did before was to try and do the finite element derivation of a stiffness matrix. Now, in finite element analysis, you're solving for the unknown displacements. But to solve for the unknown displacements, you need two things. You need stiffness matrices and what? You need loads. You need force vectors or load vectors. So what I want to do is if you go back, let's look at load vectors. And this will be quick. Okay? If you look back to our derivation, our load vector was, we said P plus the triple integral over the volume of N transpose times F plus dV plus the triple integral over the volume of N transpose times our surface tractions. Maybe I should know. That's the surface integral. Sorry. ds. Okay. Now, if you want to think of this to try and get some analogy to beam analysis, P is essentially your joint load vector. Those are the loads that are applied directly on the nodes, or direct, like what is the force at node 1, what is the moment at node 1, what is the force at moment 2, etc. Those are nodal loads. These other two are loads along the member. Now for beams, primarily all we care about are things like distributed loads, triangular loads, and what have you, right? So for beams, what I should say is we can simplify this a little easier. This P vector is sort of like our Q sub j, our fixed end force vector. Okay? And this is sort of like our, well, this is our joint load vector, and this is sort of like our fixed end force vector. And we really only deal with one type of member force, and it's like a distributed load. Now, the trick that we pulled last time, how we can take a volume integral and turn it into an integral over the length, we can kind of do the same thing. Now, I propose to you that for beams, let me extend this out a little bit. I propose to you that for beams, we can say that our fixed end force vector will end up being the integral from x equals 0 to x equals L. And then, because beams really only have one, a load, like a load as a function of x, I'll say we have some load as a function of x times N transpose. And I'll call this the non-nodal load vector. And I think you'll see where I'm going with this here in a second. Okay? So bear with me. All right. Has everybody got this? Let's look at an example. Okay? Let's say that W of x is some constant value. In other words, what I've got is I've got some element, and all it has on it is a constant load over its length. Does that make sense? So we'll say that this is W of x, but that's a constant. Everybody all right with that? Okay, so the reason why I'm using a constant is because I want to be able to factor it out. I don't like dealing with all that math. So watch this. Let me find my nifty little handout here. Okay. So watch this. So I propose to you that therefore, since we're dealing with a constant, I can say that Q sub f is pull the constant value out and then integrate from 0 to L. Maybe I should clear this up and put x equals 0 to x equals L, my n matrix. Okay, but it's the transpose. Remember, n is what? 1 by 4, so its transpose is 4 by 1, right? So it's going to be, you know, a term, right? Okay, now you'll see where I'm going with here in a second. Just bear with me. Okay, so let's see. What was n1? It was 1 minus 3x squared over L squared, and it was plus 2x cubed over L cubed. Is that right? Am I doing, you tell me. Am I following this out? All right. N2 was what? It was x minus 2x squared over L plus x cubed over L squared. Oop, I messed that up. I was trying to fix it and I made it worse. All right. Next one is 3x squared over L squared minus 2x cubed over L cubed, and then what? X to the third over L squared minus x squared over L. Did I do that right? All that integrated as a function of x. Or integrated with respect to x, I should say. I'm doing that. I do that right? Let me see if I can clean up some of these exponents. That one's supposed to be a squared. Let's see. That one is supposed to be a cubed, and what have you. Now, one thing to clarify, when I integrate a matrix like this, all I'm doing is integrating each individual term. So we'll start at the top, work our way down. Okay? So now, one thing to also emphasize is, see how the W, see how I pulled that out? I pulled it out because it was constant. What if it was a triangular load? Then I couldn't pull it out, and I'd have to, you know, do all the foiling and all that. So it's just something to keep in mind. All right, so let's see what we've got. We've got W times, it's going to be a big matrix, but let's just take it out. Let's start off with the top row. Y'all walk me through this. What's the integral of 1? X minus, okay, we've got 3x squared over L squared. The integral of x squared is x cubed over 3, right? So that's going to be x cubed over L squared. And then plus 2, and that's what, x to the 4th over 4, so x to the 4th over 2L cubed. Did I do that right? All right. Next row, what do we have? We have x squared over 2. We have minus, what is that? 2x squared, so 2x cubed over 3L plus, what is that? X to the 4th over 4, so x to the 4th over 4L squared, right? Okay, the next one, what do we have? 3x squared, so that's x cubed over 3, so x cubed over L squared minus 2x to the fourth 2l cubed, and then x to the fourth 4l squared minus x to the third over 3l. Is that a fair statement? Now I evaluate that from x equals 0 to x equals L. Is that a fair statement? Okay. I'll give you all a moment. I think you'll like this. All right. As y'all are writing this down, let's just sort of think about this. When you do a definite integral, what do? You plug in the top number, evaluate, minus, plug in the bottom number, evaluate. Subtract the two, right? Let's look ahead. If I plug in the bottom number into any one of these, what am I going to get? 0. So if I plug in the top number minus plug in the bottom number, I don't even need to deal with this at all, right? I just look at the top number. Fair statement? All right. Y'all have all this written down, or you need a minute? Okay. So let me drag it up a little bit so I have a little bit more room to write. So equals. What do I have? I have W on the outside. And all I need to do is just plug in L, right? So I have L minus, what do I have? I have L cubed over L squared, right? Right? So L plus L to the fourth over 2L to the third, that's L over 2, right? Did I do that right? What about the next one? It's going to be L squared over 2 minus 2L squared over 3 plus L squared over 4. Did I do that right? You tell me. We're good so far? Next one, what do we have? We have L minus L over 2. Next one, L squared over 4 minus L squared over 3. Everybody with me? So we still have the W on the outside. Let's evaluate this. So if I have L minus L, that cancels, right? Okay. L minus L cancels. I just have L over 2, right? So, actually, watch this. Let's do this. If I multiply the W out, would I have WL over 2? What? Yeah, there you go. There we go. All right. Let's do the next one. We have 1/2 minus 2/3 plus 1/4. Anybody got a Casio? Well, what do we have? We have 6/12 minus 8/12 is 2/12 plus 3/12 is 1/12, right? So shouldn't that be WL squared over 12? What about the next one? L minus L over 2 is 1/2? Or WL over 2? Now, what is 1/4 minus 1/3? Minus 1/12. Does that look familiar? Pretty nifty, huh? Again, the microphone's expensive, so I'm not dropping the microphone, but I'll drop the marker. Pretty nifty, though, isn't it? I'll give you all a moment to write all this out. Again, I could have milked that, giving you all a moment. I could have milked that one. Beams moment. I know for some of you graduate mechanical students, this is not the last class of the night. All All right. Does everybody have this? Does anybody have any questions? Okay. Let me sort of get somewhat organized up here. Let's see. Okay. Are we good to move on, or do you need more time? Okay. All right. Before we get into our next topic, let me discuss the homework a little bit that's coming up. Now, I'm giving you a week and a half, so I'm giving you plenty of time. Okay. Let me pass this out. All right, so here's this. One thing I will say, this is probably the only homework we will have in this class that is not an Excel homework. Okay? This is not an Excel homework by any stretch of the imagination. Okay. Here you go. All right, so to start off, this is something I really want to emphasize so that you all understand what you're looking at. We are looking at a bar element for this problem, but we are not looking at two elements with three nodes. This is a single element, and this single element has been defined with three nodes. In other words, when we assume our displaced shape for this element, we are assuming that for this element we know three values, not two. Okay? So we're dealing with a three-noded bar. So our displacements, well, we have a U1, U2, U3 on each node. Okay? Make sense? So because there are three nodes, and because we have three constants associated with that, I want you to assume the following displaced shape. For the bar element that we did before, we just had C0 plus C1x. For the beam, this went all the way to x cubed. Here, C0 plus C1x plus C2x squared, we're going to assume that the displaced shape follows a parabola. Okay? Now, what I want you to do is I've got a series of tasks that I want you to do for this element. Number one, I want you to tell me what these three constants are, C0, C1, and C2, using these boundary conditions. That the displacement at x equals 0 has to equal that, the displacement at x equals L over 2 has to equal that, and the displacement at x equals L equals this. So three equations, three unknowns. Okay? And then once you get your constants, you should be able to organize them into shape functions. So you should have a vector of U1, U2, U3, and a bunch of stuff multiplying that out. Those will be your shape functions. I also need the B matrix. Keep in mind, we're only taking the first derivative, not the second derivative. Okay? And then once you get your B matrix, you can then determine your stiffness matrix for this element. This stiffness matrix will be 3 by 3. Okay? All right? We do the volume integral of B transpose CB. C is, again, just the modulus of elasticity. We pull that out. And A is your area because we're converting a volume integral into an integral over the length. So I'm even telling you how to do that. Okay? You should. Let's put it like this. All right. Here's a gut check. Let's see if we remember what are some facts about stiffness matrices. What can you tell me when it comes to a stiffness matrix? Two facts that must always be true. Somebody tell me one fact about stiffness matrices that are always true. The main diagonal is always positive. So if you evaluate K11 and K22 and K33 and you get it negative, you did something wrong. Okay, that's number one. What's another fact? They're symmetrical. So K12 better equal K21. You see what I mean? You're going to have to do a few integrals. I understand that it's a lot of alphabet soup, but take your time with it. It won't be so bad. Now, the one thing I didn't give you, and I want you to think about it for a little bit, is this last point. If a constant surface traction is applied, what is the resulting load vector? And I want you to think about that. And based on the derivations we've done before, I think you should probably be able to reason how you need to do this one, and you'll get a similar pattern as well. Okay? Is everybody all right with this? Okay. All right. Now, for timing, I have said that this will be due on, I think I'll upload it. I think it's March 1st. I'm going to say it's due. You're giving it to me on my birthday. I usually don't advertise that too much. I found out not too long ago I share a birthday with Justin Bieber. I know. You know, I couldn't get, you know, somebody cool like Einstein or something. No, Justin Bieber. That's, you know, what I'll always remember. It sucks. But I don't even really know Justin Bieber, so I don't know. Okay. Does anybody have any questions about the homework, about what you need to do? Everybody good? Okay. I'm giving you time on it. In my opinion, the amount of work on this homework assignment is not as much as the beam element we derived, but it's the same process. Now, the big thing you'll want to pay attention to is don't do the things on your homework that were specific to beam elements. Like when we took the second derivative between the N matrix and the B matrix. Don't do that because it's a different problem. It's a different set of mechanics. You're not dealing with beam mechanics. You're only dealing with bar mechanics. So it's a different deal. In the world of finite elements, if you're ever doing any research on the topic and you hear the term C0 continuity plus, or C1 continuity, if you ever see that, C0 versus C1, C1 continuity elements are elements like beam elements where you have to match not only the displacement but the derivative of the displacement. Bar elements are C0 elements. You only care about the displaced shape. More elements yields a more accurate result. So that's sort of how that works. All right, everybody good? Okay. Before I hand these out, just one quick thing. We're going to talk about Gauss points in this slideshow. I just emailed you all a Excel file with Gauss points on it. You don't know what I mean by Gauss points. You will here in a little bit. So let me pass this out, and we will talk a little bit about Gaussian quadrature and what it means and what's the purpose. Why do we care about this stuff? It all will make sense here in the not too distant future. Here's that. More for you. More for you. More for you. Okay. So let me sort of shift F5 that. Okay. So to summarize where we're at so far, we're here. Okay. In other words, this whole semester so far has really been enveloped with a single equation. The fact that stiffness times displacement equals the load applied. And that's been the spirit of everything we talked about this semester. The difference between a direct stiffness approach and finite elements is simply this: how you get the stiffness matrix, how you get the load vector. Before, it was literally take the bar, yank on it, record its resulting forces. Now we've got a little bit of a different approach. We actually integrate these assumed displacements and their respective functions over the volume. Is it a lot more math? Yeah, but one of the nice things about it is that once you do it once, you never have to do it again. In other words, when you all start using programs like Abacus or ANSYS or LS-DYNA, ADINA, whatever, you'll hear a lot of finite element programmers refer to what they call a library of elements. And the idea is, you know, let's say you open up something like Abacus. Abacus will already have something like a 3-noted bar programmed into it. The idea is they've already done all the derivation. You'll never have to do it again. But I do want you to understand it so that you get a grasp on the process, which is why I'm having you do this homework. Now, this is this formulation of a stiffness matrix and a load vector is really seminal to everything that we do in finite elements, and we can use this methodology and this formulation to derive any elements, simple elements, complex elements. The same process works. That's why finite elements is a superior way of doing these things. Now, just to recap, I like to use our 2-noted bar as the benchmark example just because it's so simple. It really is the simpler, one of the simplest elements that we use. I'd argue that just a spring where those values are k's, that's probably the simplest element we can use. But if we go back to our investigation, our K matrix is the volume integral of B transpose CB, which we can simplify, and we get that 2x2 matrix. And we can also just sort of elaborate these shape functions. Okay? Now the big problem that I'm going to talk about here in a little bit is this. This cannot integrate. This is a computer. It can't integrate. That's not what these things are designed to do. Yeah, sure, you can go to a site like Wolfram Alpha, and it's got some fancy computer algebra systems programmed into it where you can plug in, problem 2 on your Diffie-Q homework, and it'll do some work for you. I know things about stuff. But there are systems like that. But it doesn't, let's put it like this. Sites like Wolfram Alpha and things like that, they are clever because what they are doing is forcing computers to do things that they don't want to do. These machines, I know that you can play World of Warcraft and watch YouTube videos of Jimmy Fallon and all this stuff. The long and short of it, these things were designed to do two things: count and add. And in all honesty, that's really what they're doing when you get right down to the fundamentals of it. Now don't get me wrong, they can do it damn fast, but that's all they're doing is counting and adding. Okay? So what I want to do and what I want to ask, maybe I should put it like this, is there a way we can turn an integral, which is honestly a complex linear operator from calculus, can I turn this into counting and adding and still get the same answer? And the answer is yes. There are a number of numerical integration schemes that you could use. I'm going to show you one that's very, very popular for finite elements. It's very straightforward. But let me go into this. Let me go back to, let me see where I want to go. Actually, this is fine. This is fine. Okay? If I look at this right here, I want to pay attention to this. This u of x is 1 minus x over L and x over L, and then u1, u2. These are shape functions, right? Now, one of the things about these shape functions is that they are a function of x, right? And our limits being from x equals 0 to x equals L, okay? Now, I'm going to do a little bit of a magic trick right now, and I'm going to make a substitution, and you're going to go, where in the heck did you come up with this substitution? You'll see why I'm doing this here in a second, okay? So just bear with me. But I'm going to come up with a new variable. Instead of making these shape functions be functions of x, I'm going to make them functions of a new variable. This variable xi, okay? And I'm going to say that for a given value of x, I calculate xi by saying 2x over L minus 1. Is that a fair point? I'm making that up. And you'll see, this is a very particular value for a very particular reason. You'll see where I'm coming up with this here in a second. But is everybody okay with this? Now, you've done substitution in calculus before, and if you have it's like u/du substitution. I know you've done that before, remember, in calculus. So here's my xi, my d xi, I just take the derivative. So 2 over L and then dx, right? Everybody okay with that? My point is, the reason why I'm doing that is I can turn these shape functions by taking, this and plugging and chugging and rearranging. I can take this and plug it into that, and I can get the same answer. So how am I getting from this line to this line? I'm just plugging these values in and chugging it out. Is everybody okay with that? Everybody good? Okay. Now, can we do these work? Let me sort of illustrate this a little bit. Now, one of the things I'm going to do right off the bat is I want to derive my B matrix. Now, in order to derive my B matrix is still derived using the derivative of the displacement with respect to x, because strain is still the change in length over the original length. But because I've done a change of variable, I've got to break out that old chain rule. Remember that? Well, it's been a while since we've done that. But I've got to do the chain rule. Now, my point in doing this slide is to show that not only can you change variables, but performed correctly, you can use these variables to not only get new N matrices, but new B matrices as well. Everybody okay with that? So far, so good? Now, you might go, well, Dr. Michelson, why are you making this complicated? Why are you going through all of this junk to complicate the problem? I thought bar elements were simple. They are, okay? But what I'm doing is trying to do a change of variable for a very specific reason. And it's all about this integral, okay? Specifically, the limits. The limits on that integral are from x equals 0 to x equals L. I want to do a substitution such that I change those limits. That's what I'm really after, okay? Now, if you go through and evaluate the limit at x equals 0, go at x equals 0, what do you get for xi? Well, it's 2 times 0 over L minus 1. It's minus 1. Everybody okay? Now, what do I get for L? 2 times L over L is 2. 2 minus 1 is 1. Okay? So, my point is that I have taken this and converted it into this. It's the same integral, and it will give you the same answer. But instead of it being an integral from x equals 0 to x equals L, it's an integral from minus 1 to plus 1. Does everybody see that? That is really critical, because the numerical integration scheme I'm about to show you is all based on computing integrals from x equals minus 1 to x equals plus 1. I can get you an integral in Excel like that. You give me the most complicated integral you can think of. And if the limits are from minus 1 to plus 1, I will get you the answer like that. Guarantee it. Okay? Because that's one other complicated point about integrals that might be worth mentioning is, it's not, integrals aren't like derivatives. I can write a really, really complicated function, and you can take the derivative of it. You can take the derivative of anything. You might have to employ a boatload of chain rules and product rules and quotient rules and what have you, but you can take the derivative of it. There is a point, however, analytically, when integrals become impossible. You can't do them. And you've got to rely on other methods. So that's where this comes into value. Now, so is everybody all right with that? Let me take a break. Everybody good with that so far? Now, one thing I will point out is you've done this before and you've seen this before. When you do change of variables, sometimes you have sort of a little term left over that makes the variable substitution make sense. Okay? For instance, our K matrix used to be just B transpose times B, but now it's B transpose times B, and we've got this L over 2. Why do we have this L over 2? Because our variables and our limits change. And in order for the algebra to make sense, you have to have another term in there. Okay? We have a very particular name for that term in the world of finite elements. We call it a Jacobian. Okay? Now, does it still work? If you go through and do all of this and carry the integrals out, you'll still get the same answer. So that's just me providing you the guts of the operation to show you, yeah, it works. Okay? Everybody all right with that? Okay. Excuse me. So this is for our bar element, the idea that we converted an x equals 0 to an x equals L integral to a minus 1 to plus 1 integral. And we did that through this transformation. And there was sort of a piece of algebra left over at the end. For a bar element, it was L over 2. Okay? In general, in 3 dimensions, this is our general expression for a stiffness matrix, but what we're really going to want to employ is this. What is the difference? They're all integrals from minus 1 to plus 1, and that's where numerical integration comes into play. These things, they love to count and they love to add, okay? But I mean, that is what they were designed to do. Now, if you notice, anytime you go from here to here, there will always be a term left over, just like there was up here. That is called a Jacobian in our world, just so we're clear, okay? And it's just that translation from one system to another, and that's what it is. Everybody good? Okay, now, why the minus 1 to plus 1? because of numerical integration schemes. Now, you all have done numerical integration before. I promise it. You've done things like trapezoidal rule, Simpson's rule, stuff like that. Is this going on, Lossy? You all know what I'm talking about, right? Okay. Has anybody ever heard of Gauss quadrature before? Have you ever heard of it? Have you heard of it? Okay, all right. This is a really nifty little trick. I was surprised when I was in grad school and I took finite elements, I was surprised that I hadn't heard of it before because it's incredibly simple. I mean incredibly simple, okay? What we do is we take an integral of some function and we convert it into a sum, okay? Now that sum is a function of weights and sampling points, okay? Now I'm going to, here in a little bit, just give you the weights and give you the sampling points. Nudge, nudge, wink, wink, I kind of already have because they're in your email. I emailed them to you earlier. But I want you to at least have a general understanding as to where they come from, okay? So the idea behind Gaussian quadrature is the following. We have some weird complex function that goes from -1 to +1. And what we're really after in this problem is the area under this nonlinear curve. I mean, we're sort of going outside of the world of finite elements and we're going back to just straight calculus. What are the two fundamental geometric problems that you deal with in calculus? What's the slope of the tangent line? That's where the derivatives come into play. What's the area under the curve? That's where integrals come into play. And the fundamental theorem of calculus states they're related, you know. All right. So, excuse me. Going to this, the idea is I've got this weird, funky, nonlinear function and I want to determine the area under this curve. I propose to you that I can come up with a different region, this blue region. And the area under that blue region will very closely approximate the area under the curve. Like, think about it like this, like these little, wedges outside, like you could cut those out and they about equal the area in here and it all kind of balances out. Okay? So we have 4 total unknowns. For this, we're dealing with what's called a 2-point integration scheme. We evaluate the function at 2 different points and then multiply those evaluations by a given weight. So we have 4 unknowns. If you're dealing with 2-point integration, you have 4 unknowns, the 2 sampling points and the 2 weights. Now what I mean by that is, our limits are from -1 to +1, but there's some magic, set of points in between that range that we evaluate the function at, and then when we find those points, how much do we weight them? That's what we're after. All right? So if we were dealing with 1-point integration, we'd have 2 unknowns, the weight and the sampling point. If we were dealing with 2-point integration, 4 unknowns. 3-point integration, 6 unknowns. Kind of get the pattern? Okay, let me show you how we derive these terms. It's actually pretty simple, okay? The answer is polynomials. And what we do is we assume that our function takes some polynomial form, which actually has some logical backing if you think about it. I mean, y'all remember that whole Taylor series and Maclaurin series and all that stuff and power series? Remember, you could take something like a sine, a cosine, a tangent, and you could represent it as the sum of a bunch of polynomial terms, right? So it's not like it's completely out there to make an assumption about this. Everybody good? Now, what I'm doing here is I'm taking integrals of increasing orders of polynomials. So I'm integrating from -1 to +1, but I'm doing, okay, like what's the integral of 1 from -1 to +1? It's 2. What's the integral of x from -1 to +1? It's 0. What's the integral of x squared from -1 to +1? What's the integral of x cubed? And so on. See how I'm doing that? Everybody okay with that? Okay. Now, let's start off with a simple derivation. Okay? So, if I integrate from -1 to +1, if I integrate this one, I get 1. Now, how do I do that with a Gauss scheme? I take the weight times the function plus the weight times the function, 2-point integration. What about x? The weight times the function, x squared. weight times the function, weight times the function. So see how I'm doing like W1 plus W2, WX plus WX, WX squared plus WX squared, WX cubed plus WX cubed. And I'm going down until I've got 4 equations and 4 unknowns, right? Everybody okay with this? Now, these 4 equations and 4 unknowns, if you evaluate them out, you will get that the 2 weights need to be 1 and the 2 sampling points need to be plus or minus 1 over the square root of 3. Now, if you keep doing that for 2-point integration, 3-point integration, 4-point integration, 5-point integration, what have you, that's what you get. Okay? That table that you see right there, those are Gauss points. Okay? So let me see if I think this website still works. I hope it does. So this website, yeah, I mean, you can find this stuff all over the place. Yeah, this website goes a little nuts with it. They go all the way to like 23-point scheme integration. In no way, shape, or form do we use anything that rigorous in finite elements. But it is very common to see like a isoparametric element, and it might be 2-point integration or 3-point integration. The reason why I'm doing all of this is because when you all run Abacus or ANSYS and start saying what integration scheme that you're using, you actually, now you know what it's talking about. Okay? Everybody okay with this? All right. What I want to do is, let's see, I might actually take a break and we'll hit this up next time because I want to take my time with this. I really think this is a valuable exercise. But what I want to do is do an integral that's very straightforward and then do it using numerical integration and see if you can see the difference. So we'll pick this up next time, but what I want to do is I want to look at this integral. We're going to integrate e to the x. Okay, what is the integral of e to the x? It's e to the x. Okay, so evaluated from -1 to +1, you're going to get e minus 1 over e. So remember the natural base is like 2.7, something, whatever. If you do the math, this integral is about 2.3504, whatever. We're going to do this using a few different integration schemes. We'll try 2-point integration, we'll try 4-point integration, or what have you. Now, this is one-dimensional in nature. We are only taking a single integral. We're then going to ask, how do you do a double integral, or how do you do a triple integral? Why does that matter? Because in finite elements, we tend to do 2-dimensional analysis, 3-dimensional analysis. If you're doing a, let's say, I don't know, an analysis of a V6 engine and you use brick elements, those are 3-dimensional integrals. So that's what it's doing. I really want you to have that understanding before we open up FEMAP later on. All right, everybody good? All right, that's all I've got for today. I think I'm going to call it early. I want to let this sink in, and we will continue this next time. Okay.